Today we will learn why E equals mc squared. This can be derived if we study further on the four vectors. The most elementary fundamental four vector that we have just learned is the four displacement. Four displacement. That is just a space-time event. In general, it is ct 3t, keeping the transverse direction to be vanishing. In the rest frame, these coordinates are simple, c tau 0, 0, 0. We use x mu, where Greek letter indicates the index 0 for time components, 1, 2, 3, 4 spatial components. Before we investigate the nature of the four vector, it is nice to look into the three vector structure under Galilean transformation, because it's almost a carbon copy of the theory, except that the scalar product is defined in a Minkowski space 4 vector. So let us first review the Galilean transformation properties of the three-dimensional vectors defined in the Euclidean space. First of all, in Galilean transformation, time and mass, both of them are invariant quantities, so they are always the same in any inertial reference frame. If we consider a vector, the vector has components. EI hat is the unit vector along the Cartesian axis. Xi will be the ith component, so I is to be summed from 1 to 3. On the rotation, this coordinate transforms into x prime, where x prime vector is using the same basis. The coordinates I runs from 1 to 3. Coordinate may shift. The transformation rule is determined by the rotation matrix capital R. Under this rotation, this transformation rule is always the same for any vectors. That means this matrix element is independent of any point, independent of coordinates in a specific coordinate system. If we want to compute the displacement of a particle from here to there, and this is the measured at time t1, and the later time t2 that is greater than t1, this red vector, the red arrow, indicates the displacement from the initial position to final position. The final position vector subtracted by the initial position vector is the displacement. Because every component of initial vector and every component of final vector, they both of them satisfy the same transformation rule on the rotation. You can see this triangle, they are congruent. What we have done is we have rotated every vector with the same angle. This is initial direction. This is the angle theta. It used to be there, x2 used to be there, but we have rotated the vector by an angle of theta. Because initial and final points are both making a transformation following the constant matrix elements, rotation matrix, or we can define the displacement, we can find this displacement is the same, follows the same rule. I mean, x1 I j rij x1 prime I equals sum over j equals 1 to 3, something like that. And the same rule applies for this final point equals the sum over j rij x2j, something like that. If you subtract these two, subtract x2 prime, if we compute x2 prime minus x1 prime, what we obtain is this. So before making a difference, before computing the difference of the two vectors to evaluate the displacement, we have the rule, but this rule, rotational rule, is always the same. And then we apply the constraint that t prime equals t for the Galilean transformation. Then we can divide both sides with the delta t, and on the right side we just keep it as delta t, and left side we replace this delta t prime because of the invariance of the time on the Galilean transformation. We can replace this one x prime divided by delta t. Therefore, this relation is directly derived from the difference relation. What we have done is just multiplied 1 over delta t to the left hand side and right hand side simultaneously. Because of that, this is the velocity in a frame S, and this is the velocity in another frame that is S prime. And they have a relative velocity following the Galilean transformation. As a result, x is a vector, but this x is a position vector, displacement is a position vector, and then if we divide this displacement as a free vector with the Galilean invariant quantity that is a time, then what we get is velocity, and velocity is also vector. That means a vector rotational property of the velocity is the same as the displacement, and the rule for the displacement is the same as that of the position vector. In a similar manner, we can go further. The change in velocity, a new reference frame is I component is Rij Vj sum over j runs from 1 to 3. We can delta, and then divide both sides with the invariant quantity that is delta t in the Galilean transformation. What I would get is the acceleration. Acceleration is another vector that transforms on the rotation, just to multiply the same rotation matrix R that has been used for the rotation of position vector, rotation of a displacement vector, rotation of the velocity vector, and rotation of the shift in velocity vector, rotation of the acceleration vector. So x, v, acceleration are all vectors, all three vectors, three vectors. Three vector means all vector defined in the Euclidean space. In addition, in Galilean transformation, mass of an object is invariant under Galilean transformation. Therefore, if I multiply mass to the acceleration, what I would get is mass times acceleration, that is a force. Therefore, displacement, velocity, acceleration, and force, everything is three vector. Three vector means on the rotation we find they follow the same rotational properties. This logic is directly applied to the how to find out the four vectors that has the same property, just like the case of the four displacement on the Lorenz transformation. Now we are ready to study for velocity, and we shall find that the zeroth component of the for velocity is closely related to the famous formula E equals mc squared. So we just have reviewed the way to find vectors out of known vectors. For example, displacement can be used, and the invariance of time and mass in Galilean transformation was used to find that displacement x derives a velocity as another vector, multiplying mass to velocity. The linear momentum is another vector, and we take the derivative, time derivative, to find acceleration is another vector, and multiplying the acceleration by mass, ma, this is a p, and this is the force, is another vector. Everything satisfies the transformation rule. The vector, ith component of vector is Rij Vj. This is a prime, and sum over j runs from 1 to 3. In a similar manner, we'd like to construct useful full vectors out of the four displacement. Our starting point was, well, there's a typo. C should be removed. Wait a second. So this C should be removed. The time dilation states that the moving clock shows the time t that is longer than the proper time tau, that is measured by making use of a clock fixed in a reference frame in which an observer is stationary. Okay. The gamma factor, Lorenz factor, is completely determined by the parameter beta, that is the speed of an object divided by the speed of light. Velocity is the time derivative. This is time derivative. This is not the derivative with respect to the proper time, but the derivative with respect to time. That includes the time dilation. So an object at time t has for displacement ct and x vector. If it has a constant velocity, it should be v times t. So this is for displacement x mu. We use the Greek letter to identify the forward vector is working on the Minkowski space, whose square or scalar product is defined by square of the time component subtracted by the square of the spatial components. The coordinates, we usually use upper indices for the usual vector defined in the Minkowski space. In the rest frame, we use unprimed temporally, and in the frame where the particle is moving with the velocity v, we use the primed system. The coordinates, unprimed coordinate represent at this moment represent the space-time coordinates in the rest frame. Hence, there is no spatial component. It is vanishing. Only the proper time goes by. In the frame where a particle is moving with a velocity v, its displacement along the x-axis is vt, and time flows with the same rate. We can factor the proper time and speed of light out. In that case, because t equals tau times gamma, c tau, as soon as we factor this c tau out, the time component becomes gamma and spatial component becomes beta gamma. As we already have stated, gamma squared subtracted by gamma squared beta squared equals gamma squared 1 minus beta squared, and actually gamma squared 1 over 1 minus beta squared, hence it is 1. Something squared subtracted by something, that is always parameters by cosine hyperbolic and sine hyperbolic. Alright, so that's the reason why our Lorenz boost matrix from the rest frame to the booming frame was gamma, gamma beta, gamma beta, gamma. Or if we make use of the hyperbolic cosine and sine, this cosine hyperbolic phi, sine hyperbolic phi, sine hyperbolic phi, and cosine hyperbolic phi. There's no sign difference at all relative to the rotation matrix that has the cosine, sine, and minus sine, cosine. Again, the determinant of the Lorenz boost matrix and determinant of the rotation matrix are both equal to 1. Sure, this is not unique. I mean, there are some matrix that has a negative -1 determinant if it includes the reflection of a single coordinate, or odd number of that a series of odd number of such kind of reflection transformation. Anyway, the scalar product in the Minkowski space, in the Euclidean space, is defined by just the sum of the squares of the elements, and in the simplest case, the two-dimensional Euclidean space, the scalar product of itself, that is a square of a Euclidean free vector, is just can be computed by using matrix representation, just a row vector and column vector consisting of x1, x2, x1, and x2. And we have a metric tensor that defines the distance, that is just a trivial identity matrix whose matrix elements are Kronecker deltas. If we substitute in here, uh, rewriting the each component x1 and x2 component, x component and y component with the radius and the polar angle, x1 becomes r cosine and x2 becomes r sine. And using this, we can find that the the determinant of r equals 1 says that this square is always invariant on the rotation. In a similar manner, except that the distance is defined in a different way in the Minkowski space that has we have a relativistic triangle C tau, Ct, Vt. And here we have the invariant relation Ct squared minus Vt squared equals to C tau squared. And C tau squared is actually C tau squared minus 0 squared. That means the time component square subtracted by spatial component is invariant on the Lorenz boost. So in any inertial reference frame, square of time component subtracted by the spatial component square is invariant. That means x dot x, 4 vector. The square of a 4 vector is defined in a different way in comparison with the square defined in the Euclidean space. And that should be invariant in order to write this kind of square in terms of matrix representation. What we would have is just put CTVT as a transpose and CTVT. If I want to get a result, the CT squared minus a VT squared, what I need to insert in between is identical to the Kronecker delta, except that I need to put a negative sign on the 2 element. That's a 1 1 element 0. This is 0 0 element 0 1 element 1 0 element and 1 1 element. So we call this one to be the metric tensor. In here, this one, in this one or this is the metric tensor. Identity matrix is the metric tensor. Metric tensor means this one originates from meter, measuring tensor. Distance, definition of distance is closely related to the definition of a scalar product. When we want to define the distance, we need a scalar product. And the scalar definition of the scalar product in the Euclidean space requires the metric tensor identity, and definition of the scalar product defined in the Minkowski space requires the metric tensor of this kind of form. Time component is a positive +1, and all the spatial components becomes -1. Anyway, under this transformation, Minkowski 4 vector has the scalar product invariant under any kind of Lorenz transformation. We have seen the invariance of this scalar product on a single direction along the single direction according to Lorenz boost. However, it is also invariant on the rotation and mixture of rotation and boost. That is out of the scope of our class, so let me just stop going further. All right, just like what we have done with the rotation using Euclidean three vector, we can consider the Lorentz boost of space-time coordinate that is called the forward displacement on the Lorentz transformation. What I have to do is just multiply this matrix 2 by 2 matrix that is either parameterized by this or parameterized by the hyperbolic cosines. If there are two consecutive events with different time and spatial position, then we subtract the two, the one event and two event. If the event two happen in a certain inertial reference frame later than one, then we just compute the difference of the displacement to find out the forward displacement. Finite differences for displacement because each of them, each x1 and x2, both satisfy the Lorentz transformation. The difference must satisfy the same kind of relation. This is parallel to the computation of the displacement delta x. This is a prime. Next step, when we obtain the velocity in the Galilean transformation, we made use of the fact that t prime equals t in the Galilean transformation. But this is not the case if we consider the forward vector for displacement, because t is gamma tau, and that is not the same as the perfect time. So time depends on the frame of reference. So this step doesn't work at all if we consider the Lorentz transformation. If I want to keep the rotational transformation the same, I can use this strict condition that time is invariant on the Galilean transformation. But in our case, time is not invariant. So if I want to divide both sides by something, I need to divide this formula by a single time that is not transforming under the Lorentz transformation. The time scale that does not depend on the frame of reference is the proper time instead of the time, because time in here and time in here are defined in a different way with the multiplicative factor gamma. This is the very big difference between the Galilean transformation and Lorentz transformation. The time scale I have to put in on the denominator is not t, but it should be delta tau. And delta tau is proper time that is invariant on the Lorentz transformation. In fact, if something is moving, its displacement expressed in terms of time, so it should be gamma tau. If I want to compute the velocity, that is not the spatial component of a Lorentz invariant quantity. If I divide this one by t, what I would get is a v. But that is not the 4 vector. Instead, what I have to do is divide this one by, instead of t, we need to divide it by tau to find the Lorenz invariant, Lorenz covariant for vector out of the displacement. So we introduce a vector. This is a CT. VT is the column matrix representation for a column vector representing the for displacement. Delta x versus C delta t and V delta t. Delta x should not be divided by delta t. Instead, we divide it by delta tau. But we know that delta t equals gamma delta tau. So gamma is pulled out. C V. This is the 4 velocity. We remember C tau 0 boost to have CT VT. This is the general form of 4 displacement, and the general form of the 4 velocity is the derivative of the 4 displacement with respect to not respect to t but respect to tau. Therefore, this u mu equals dx mu d tau, and the final result is c gamma v gamma. This additional factor, the Lorenz factor, makes this one to be Lorenz covariant 4 vector that can be found by squaring this. If I square u square, that is c gamma square subtracted by v gamma square, that is gamma square, c square is 1 minus beta square. We know that 1 minus beta square is the reciprocal of gamma square. This answer is c squared. Therefore, for velocity u has a square, its value is the speed of light squared. Is invariant under Lorenz transformation. Now we know two kinds of 4 vectors. The first one is the 4 displacement. This is a Lorenz invariant because the x squared equals ct squared minus vt squared and c tau squared gamma squared 1 minus beta squared, that is c tau squared. And c tau squared is c tau squared minus 0 squared, that is the x rest frame squared. Squared is invariant under Lorenz transformation. Out of this, we have constructed another full vector that is mu equals dx mu over d tau. That is c gamma v gamma, and square of the forward velocity equals c squared. Just like what we have done with the derivation of the velocity from the displacement, according to Galilean relativity, I can divide this one by t. Here we have divided by proper time tau. After we have obtained the velocity, we use the invariance of mass under Galilean transformation to multiply m to the velocity to obtain the linear momentum. That is another kind of vector that satisfies the rotational properties just like the displacement 3 vector. Our next step, we have obtained x mu for displacement, that is CTVT in general. We now have obtained the u mu, that is c gamma v gamma. Now, next step is to multiply the load here divided with by proper time. What we have to do is multiply some parameter that has a scale of mass, but which is Lorenz invariant. What I would multiply is m0, that is called rest mass. This is proper time, that is another way is rest time. The clock is fixed. The clock is at rest. The clock is stationary. A particle is at rest. Then that mass is called rest mass. We shall find the mass of particle increases as the particle moves, its speed increases, the mass will be increasing arbitrarily large depending on the velocity. Even though it cannot surpass the speed of light, as it approaches the speed of light, the mass of a particle grows without bound to the infinity. Anyway, just like the time dilation does, mass increases. And the only time scale that is independent of Lorentz transformation is proper time, just like that. The mass that is invariant under Lorentz transformation is the rest mass. And let me multiply the rest mass to the full velocity and look into this is called the forward momentum. Look into every component of a forward momentum for their physical meaning. And at the end of the day, we shall find the time component of the forward momentum represents the energy over speed of light. And that energy is E equals mc squared, where m is the rest mass and 0 multiplied by the Lorenz factor. This is an advanced explanation for how to find additional four vectors out of known four vectors. So if you have time and you have intellectual curiosity, and you can study further about this. But for the time being, I'm concentrating on a very simple nature, invariance of time, invariance of proper time, that is independent of frame of reference. These are the summaries of what I have already uh, told you about the four displacement and the derivative of a four displacement with respect to time may reach, you can square this. This one is c squared. You can square this. This is a c squared minus v squared. They are different. So x mu is a 4 vector, but x mu derivative with respect to time is not a 4 vector. It is useless. Non-invariance of the square. So this x mu dt, this is not a 4 vector. Instead, x mu derivative with respect to tau is a 4 vector called u mu, that is a 4 velocity. And then its squared, u squared, is always speed of light squared. For displacement in a rest frame and moving frame. For velocity, rest frame, and moving frame. In a moving frame, C gamma, V gamma, the rest frame, gamma reaches 1, gamma reaches 1, and V reaches 0. Therefore, in the rest frame, this 4 velocity is a trivial 4 momentum. There's a C comma 0 vector. So now we are ready to consider 4 momentum. 4 momentum is a momentum obtained from the 4 velocity multiplied by the rest mass of the particle. And 4 velocity u mu in the rest frame is 0, and moving frame it becomes a C gamma V gamma. If I multiply m0 to the 4 velocity, what I get is m0 gamma c as the first of the time component, m0 gamma v as the spatial component. If I look at this first component, it looks like m0 gamma c squared over c, and the spatial component m0 gamma v. This is m0 v divided by 1 minus c squared v squared. At the moment, we think we can define mass that depends on the velocity of a particle, actually the speed of a particle. This is not invariant. It is varying depending on the speed of an object. If I define the mass depending on the speed, therefore velocity can be written into mc squared over c and mv. It is very similar to the non-relativistic linear momentum, except that it is absolutely different from it because we have additional factor in the limit beta goes to 0 and reaches m0. So that reproduces a non-relativistic theory that momentum is just rest mass multiplied by the velocity. However, in the region where beta reaches 1, in extremely fast case, it is the non-relativistic theory completely breaks down. So we hope this seems to be the actual momentum that we measure in real world. And in most cases, velocity is very small in comparison with the speed of light. We can treat this one to be rest mass multiplied the velocity. However, because any object, any massive object that can accelerate, however, that they can never reach the speed of light. That means its momentum, although its momentum goes up, the velocity can never pass the speed of light. That means mass is the source, increasing mass is the source to absorb all of the energy that is accumulated to the system. That's the reason why it can never reach the speed of light. Therefore, the spatial component of the form momentum can be understood as a momentum, linear momentum, relativistic linear momentum that is gamma 0, m0 gamma velocity. And this velocity is the normal definition of the velocity that we used to know. This definition is the same, but this one is not the Lorenz covariant expression. However, that is included after multiplying it by the Lorenz factor. This free momentum p that becomes the spatial component of a four momentum p mu, something that we still don't know, but this is a linear momentum, and linear momentum is a mass times velocity. However, this mass is not the rest mass that we used to know, but is the rest mass multiplied by the velocity divided by a number. So now we understand what the spatial component of this four momentum is. However, we still don't know what the zeroth component, that is mc squared over c, or m0c squared over c multiplied by this additional factor coming from the Lorenz factor. That is the last part and the most important and most exciting part of this lecture. We have finally reached the last stage to identify what this p0, the time component of the form momentum, means. Previously, We began with x mu for displacement, and then we have derived u mu, that is the forward velocity, that has been obtained by taking the derivative with respect to Lorenz invariant time, that is called the proper time. And then we have derived the forward momentum p mu by multiplying the forward velocity by the rest mass m0. That forward momentum has the components m gamma c for the time component, m0 gamma v for the spatial component. The spatial component p vector was m0v vector divided by square root 1 minus v squared over c squared, and the reason the presence of the Lorenz factor makes a crucial role, that even if we pour whatever amount of energy to a massive particle, the mass of the particle grows up with the factor of Lorenz factor. So even though the energy of the particle has no unbounded, and it is diverging to infinity as it reaches the speed of light. Therefore, the spatial component of the momentum is well understood, in that it makes the particle never reach the speed of light and never pass the speed of light. And then finally, we have a curious term, that is the time component of the forward momentum, P0. P0 is gamma M0 gamma C. We'd like to interpret this one as an energy scaled by in units of speed of light. That means M0 gamma C squared divided by C. So we are interested in what it means by computing the kinetic energy of the particle from the rest frame to the frame in which its velocity is v. We have defined the particle's mass, that is moving with the velocity v, is expressed as a product of the rest mass multiplied by the Lorenz factor. Let us compute the force on that particle. We do not have to consider the full force at this moment. Full force is really important in the next level, but at the moment, the spatial component P, that is gamma m gamma 0 v, is identical to what we measure in real world with the usual ruler and clock. What we want to do is compute the force, and then with that force we can find the work, just following the work kinetic energy theorem of Coriolis. So free momentum, spatial component of the forward momentum is a free momentum, It's an ordinary time derivative. It's not the time derivative, it's not the derivative with respect to the proper time. It's derivative with respect to time in ordinary sense. So this force is not the spatial component of a full vector. This force is not the spatial component of a full vector. Very important. It is just what we measure in real world. Okay, and we would like to substitute this force in here to compute the force that's given here. Momentum, time derivative. As we know, both m0 and speed of light, they are Lorenz invariant factor. And we pull these factors out. Then what I get is this velocity is rescaled by in units of speed of light, then v over c. That is a c beta vector. Therefore, the gamma vector is written in this form, and then velocity after the rescaling by the speed of light, the force is expressed as the ordinary time derivative of beta over square root 1 minus beta squared. All right, to simplify the calculation, what we want to do is we notice that this dt appears in the denominator both sides. So we can just remove this simultaneously by changing the variable from time to the momentum itself. So differential of the linear momentum scaled by Lorenz invariant quantity, that's m0c, then the left-hand side becomes the dimensionless. This is a pure number that does not carry any physical dimensions. That greatly simplifies our intermediate calculation. The right-hand side is total differential of a beta vector divided by square root 1 minus beta squared. What we want to do is to compute the kinetic energy of the particle from the rest frame to we boost up this particle. Whatever energy is supplied to the particle, if it acquires energy, then it is revealed as the kinetic energy. In non-relativistic theory, that kinetic energy is 1/2 m0v squared, but this is completely broken in the relativistic limit that we are concerned. So force from the relation of the force, we have found the total differential of the linear momentum in this way. All right, the calculation of kinetic energy is a calculation of the work. Work is a force times a displacement. And this displacement is true from this is the x from rest to the velocity v. We find the momentum is the time derivative of a linear moment. We change the variable from x to velocity, mean dp over dt, dot dx that can be written in the dp dot. Okay, so here dx integral becomes a dp integral. So dp is this one, and velocity appears in here. So velocity scalar product with change in the linear moment. Just like what we have done here, it's better rescale the dimension for quantity. For example, the momentum can be rescaled with p can be rescaled with m0c p. Then this one is a dimensionless quantity. And we have velocity. Then velocity can be rescaled with the speed of light. So v can be replaced with c beta. Again, this one can be rescaled with this m0c, and then we can multiply m0c, so it becomes m0c squared and dimensionless integral. In that case, the left side is the kinetic energy divided by m0c squared, and we end up with the dimensionless integral. At first glance, this integral looks complicated. However, we can make use of this simple relation. Derivative of a product is derivative of first factor multiplied by second factor plus the first factor multiplied by the derivative of the second factor. That means total differential of a product is differential of first multiplied by b and a multiplied by the differential of the factor b. So let us substitute, and in addition, this relation holds for vector a dot b. Total differential of a scalar product can be expressed as this one plus a dot db. We substitute a equals a beta vector and b equals beta vector divided by 1 minus beta squared. So beta dot d beta gamma, actually this is gamma, equals d beta dot beta gamma minus beta gamma dot d beta. Right? No, gamma is not a vector. Gamma is not a vector. And this is beta beta. So this is beta square gamma, and this is what? Minus a dot dA is actually 1/2 dA squared, right? So this one is minus 1/2 gamma d beta squared. Again, what we know is gamma 1 minus beta squared is 1. So what's that? This beta squared dependence, this is a gamma beta squared minus gamma beta squared plus gamma equals 1, right? So gamma beta squared equals gamma minus 1. This kind of simple algebra can be applied to simplify this integral. Okay, let's see. This is a so-called integration by parts. So we have rewritten this integral as a difference of these two, and we have made use of this relation. And this is the total total differential. So this trivial answer is just this one itself. And the second one, this is a trivial integral, the first vector. And second one, this one is a beta integral, but we can make use of this. D beta minus d beta squared is minus 1 minus beta squared, and that is 1 over gamma differential. And 1 over gamma is just 1 over gamma's differential. Finally, here I need to subtract the initial value, but initial value is initial state is beta equals 0, rest frame. So this value subtracted by the initial value, that is beta equals 0, so I do not, the minus 0 is missing, but that part doesn't matter, doesn't change the answer. And this is total differential, and this is the value at the stage when the particle acquires a velocity v, and this is the initial value when beta equals 0. Finally, we have reached the final answer for the kinetic energy scaled with the Lorenz invariant unit of energy, m0c squared. The answer is, after trivial algebra, what I would get is gamma minus 1. What does it mean by the kinetic energy in units of m0c squared is gamma minus 1? The Hamiltonian, the total mechanical energy, is the sum of kinetic energy. Here I used T instead of K. Kinetic energy plus potential energy. And it seems there is a kinetic energy that is m0c squared gamma minus 1. And I don't know Usually this is a free particle. There should not be any potential energy, but I don't know. I don't have to worry about the constant value because potential energy is not determined up to constant. As functional dependence exists that care that contribute to the actual force, but I don't have to worry about the constant addition of the potential energy. But anyway, kinetic energy is not 1 half mv0 squared, m0 v squared, but this one. This is the relativistic kinetic energy. Now, we have another way to compute this using the Hamiltonian way. But anyway, the P0 is m0 gamma c. But what we just have obtained is kinetic energy is m0 c squared gamma minus 1. So, kinetic energy divided by speed of light equals m0 gamma c. That's right, this is P0. However, we need to subtract minus m0c. Why don't we move this guy, to the left hand side? Then what I get is kinetic energy plus m0c squared divided by speed of light equals P0. M0 gamma c is P0. Now I understand. Okay, we have a 4 momentum P mu that is m0 gamma v for the spatial component and m0 gamma c for the time component. But this time component seems to be energy divided by speed of light, and that energy seems to be is identical to m0c squared plus kinetic energy, and that's what we have just computed. Kinetic energy is m0c squared gamma minus 1. What happens if a particle is not moving at all? If the particle is not moving at all, we recall that full velocity u mu is a c0. If I multiply the rest mass, m0 u mu equals mc0 vector. I can reproduce this, and this is m0 c squared divided by c0 vector. Aha! Einstein's interpretation of the Gibbs component of this 4 momentum is, alright, P0 is energy divided by speed of light. That's right. And this energy is the sum of rest energy plus kinetic energy. Kinetic energy is m0c squared gamma minus 1. Any object with its rest mass non-zero has its original energy, even though it is not moving at all. That is m0c squared. And when it acquires momentum, this rest energy cancels to find out m0 c squared gamma. And actually m0 gamma is the mass of the particle when it is moving. That is mc squared. M is the mass dependent mass, the velocity dependent mass. This is the triumph of relativity, and this identified to be the rest energy is really existing, and all kind of energy source of atomic bomb. And in reality, particles of heavy particles decay to lighter particle, and the amount of lost energy is transferred to the kinetic energy of the daughter particle. In the questions of this chapter, you will find that J psi, which is the bound state of charm and anti-charm, decays into electron and positron pair. J psi was discovered in 1974, and this massive particle, this is 3.1 GeV of the energy scale, and it decays into zero point 0.5 MeV, a pair, a very light particle. They will fly with almost the speed of light, and the kinetic energy of this light particle was they would come from the lost mass of J star. So the rest energy can be transferred into any kind of energy, especially for the decay of into a lighter particle. It is transferred to the kinetic energy of the lighter particles. Now we understand what E equals mc squared is by starting from a very simple idea to derive velocity and momentum and force in the Galilean transformation based on the invariance of time and mass in this non-relativistic theory. We generalize this idea to the four moment for displacement that directly came from the time dilation of space-time coordinates that is discovered by Michelson-Morley experiment. We just derived for velocity, that is another kind of velocity that follows the full Lorentz transformation. And we have multiplied the Lorentz invariant mass that is called the rest mass to construct another Lorentz four vector, and the spatial component is identified to be the momentum identical to a usual definition except that it has a Lorentz factor in the mass, and then the zeroth component, the time component, is now understood to be the energy over speed of light, and that energy is the rest energy m0c squared plus kinetic energy. And kinetic energy is m0c squared minus gamma minus 1, and rest energy cancels to find out m0c squared gamma. That is the mc squared, where m is the mass depending on the speed of a particle. Thank you.